monitor system. Okay.
Hi, Shaokai, sorry. There are two things. So I hope you don't mind if we record it. We would hope.
No, I don't mind.
Okay, sounds great. And the other thing is, it seems like your audio is breaking up a little bit.
Mm-hmm.
So
where was I?
Yeah, it was kind of spotty, but I heard most of it. But I wonder if this is gonna be a problem.
It sounds like either the mic isn't close enough or it's a bad mic.
Uh-huh.
How about now?
Yeah, that's much better.
Okay.
All
so
right. Yeah.
Let me just keep the microphone close to my mouth.
Sounds good. Yeah.
Can you really then manipulate the cursor and everything else you have to do with only one hand?
Yeah, I can manage to do that. Yeah. So I hope this page is clear for you. Then let me give the outline. So in the first part of the talk, I will show you that the measurement-induced phase transition is spontaneous symmetry breaking. So it is actually spontaneous symmetry unbreaking transition in replicated space. That means if you increase the measurement rate, the symmetry is restored. There are various previous works talking about this, but in this talk I will focus on SYK model. And the second part is about quantum error. And I'll tell you that quantum error is explicit symmetry breaking in the replicated space. So to talk about measurement, we need a set of measurement operator. So I call MI here. And the measurement is done by applying the measurement operator to the density matrix. For example, if we consider projective measurement of a qubit, we have two measurement operators and the projection to 0 or 1 states. So the outcome of the measurement is either 1 or 0, depending on the form probability. So if we keep the measurement record, say we know the measurement outcome is 0, then the resulting state is, of course, the 0 state. This is also by applying the M1 to the density matrix. So whenever we say we keep the measurement record, all we mean is that we know exactly which measurement operator is applied to the density matrix. So if we look at the observable that is nonlinear in density matrix, say we look at the density matrix square, then there are 4 copies of the same measurement operator applying to density matrix square. It is similar to the evolution operator. One difference is that the measurement operator can be Hermitian instead of unitary. So actually they can be any, as long as this requirement is satisfied. So we can still talk about dynamical symmetry with measurement. Apparently there is still the mirror symmetry between 1 and 3, as well as between 2 and 4. Another consequence of measurement is that local measurement destroys entanglement between different parts of the system. Say we have a chaotic circuit that can generate a volume law phase. And imagine we implement a projective measurement to all qubits, then the state collapses into a product state. There will be no entanglement between different parts. So one would expect a transition as a function of the probability of making the measurement from volume law to area. And this is indeed the case. So people have studied such hybrid circuit. So it is weak wall of 2-qubit random unitary circuit that can scramble the information over the full system, and between each layer there is a probability to make a local measurement.
What is P?
P is like you pick a P out of and
I see.
qubit you make the measurement between each layer.
And I mean, if P goes to 1, then there should be no entanglement.
That's right. And there is a finite, like PC, you have a transition between volume law and so so in this talk I will focus on 2 universality classes, but there are certainly more than that. These 2 are confirmed at least in a large scale numerical calculation. So the first type is the transition in random Clifford symmetry circuits plus local measurement. So here is a plot. It is the entanglement entropy as a function of subsystem A. And this is for different measurement rate. So if measurement rate is small, then you can see it is very clearly a volume law. While you increase the measurement rate, then the entanglement entropy saturates to a constant value. That indicates an area. So the transition is confirmed. And people can even do better. So if the data near the transition point is plotted together, they can form a very beautiful data collapse. The second universality class is for random free fermion circuits plus local measurement. So an example of that is just 2 fermion. So it's fermion hopping between nearest neighbor site. And there is a finite probability to make measurement of the local fermion density. So in this figure, let's just take L to infinity, the thermodynamic limit, and focus on this line. So if the measurement rate, which is called gamma here, so if gamma is small enough, the entanglement entropy is a log law. It's like a CFT, so you can assign an effective central charge to entanglement entropy. And if the measurement is large enough, it becomes an area law. So there's a transition from logarithmic entanglement entropy to area law entanglement entropy as a function of measurement. So this is the figure of the numerics. Moreover, the transition is again continuous. So if we look at this QSD here, this is effective central charge, and this is the measurement rate. So there is a critical measurement rate where the effective central charge vanishes, and this indicates a transition from log law to area. So now we have 2 universality classes. One is from volume law to area law. The other is from log law to area law. So our question is, can we design a solvable model to feature both universality classes? If so, how to understand them in a systematic way? Now let me introduce our model. So it's SYK chain. It is, so our model has 2 parts. The first is the unitary part. So it is basically a chain of Majoranas. And at each side, we have n Majorana fermions. And the Hamiltonian has 2 parts. The first one is nearest neighbor hopping. And the second one is 2 fermion on-site interaction. And we choose the coupling to be Brownian random. This is not so important. So this model is solvable in large n limit. And the crucial property of this model we will use is that it is chaotic. So if you look at the evolution operator that is generated by this Brownian Hamiltonian, so this is an example because we have a Brownian randomness.
So is this SYK in that you're going to like average over these U's?
That's right.
And X refers to what?
Sorry.
So you've got the IJKL indices.
Yes.
And you also have X indices.
Oh, X is the site. So I have a chain, and then I label the site by X, and these are independent variable from different sites.
But aren't IJKL also the site or no?
Yeah, so in every site, there are n of them, and I just pick randomly for IJKL from that site. You are right, for every X, there are IJKL, etc.
Oh, are the X like the different copies? So, or no,
Yes.
that doesn't make sense.
X is just the site, so at each site you have that n number of Majorana.
Oh, okay.
Yeah, I forget. Oh, sorry. It is just psi xi. Yes, it is.
Yeah. Okay. Good. But what's the distinction between like the site versus like which kind of Majorana fermion it is? Because aren't they kind of the same? Like they're just two different labels, and you just have some number of Majorana fermions, and you choose to label them by 2 indices instead of 1 index.
Mm-hmm. Well, in total you have L times n. So L is the site, the number of sites. N is the Majorana at each site. So these are independent.
I see. So the only thing that distinguishes those two indices is because that first term connects one in adjacent
That's
sites.
right. That's right.
Okay.
Yeah, the first term is the hopping. Yeah, so the property I will use is that this model is chaotic. So if you look at the ensemble that is generated by this Hamiltonian, because the Hamiltonian is Brownian random, and this ensemble can actually reach K design in polynomial times.
What is the K for the K design?
K means, say you have an ensemble and you calculate the second moment of the distribution, and it is same as the high ensemble.
Yeah, I thought K means you could reach the same result if you care only about less than K moment, but I'm just wondering what the value of K is for SYK type stuff.
It's actually it's the same. So this UT, and you have a UT dagger, and that is one design. It matches the result of high ensemble. So it's U dagger to power of K. And if that guy has a distribution that match high ensemble, you say that is a K design.
That's right, but K is an unspecified number for the moment.
Oh yeah, the polynomial times is proportional to K.
Oh, I see. The longer you wait, the bigger
right.
the K is. Okay, I see.
Yeah.
So so you've made the coefficients U and J depend on time in a random way. Are you're also going to take an ensemble average like you normally do in SYK?
You are right. That's true.
But this, I guess the averages that you've written are the ensemble averages. Yeah.
You mean this equation?
No, I meant the equations with the bars over them. Those are ensemble averages.
Yeah, this is the ensemble average. Okay, maybe let me move on. So we need a second part for our model. We need a monitoring operator. So now we just consider two copies of the chain and call them left and right. And then we pair left and right Majorana to a complex domain. So for each.
Sorry, I have another question before you go on. Can you go back to the previous slide?
Sure.
So you wrote that it's chaotic. Does that mean that the Lyapunov exponent saturates the bound?
No, no, actually in this model, because the randomness is Brownian, we don't conserve energy. So temperature is not a meaningful quantity. And
Okay,
when you talk about bound, obviously you talk about the 2 pi t bound, right?
right, yeah.
Yeah, it does not saturate the bound because there's
Okay, so when you say chaotic, then you mean like the spectrum of the eigenvalues is chaotic or something?
this is exactly what I mean. So it can reach K design in polynomial times. And the consequence of that is you have a volume law state after polynomial time.
Okay, thanks.
So we pair left and right Mirana to a complex form. Then each complex fermion spans 2-dimensional Hilbert space. 0 or 1, this is the occupation number. Then we monitor the local Fermi parity of the state. So the measurement operator is given by the projection operator to 0 or 1 state. If S is equal to 1, then this is a projective measurement, like before. Here we allow more general measurement, which is weak measurement. So we allow S to be less than 1. If we implement a projective measurement to all complex fermions in a chain, then this collapses the state to product state between different sites. Imagine we cut the chain into 2 parts, A and B. And for this product state, there's no entanglement between A and B. So we expect a transition from volume law to area law by increase the measurement. Since I'm going to use effective action approach, let me introduce the path integral in 4 contours. So given a measurement record, say J1, J2 to JT, a quantum trajectory of density matrix square is shown here. So basically, initially we have 2 density matrix, and we evolve using Brownian SYK Hamiltonian, and then we make measurement. Because we know the measurement outcome, so the first measurement outcome is J1. It is the MJ1 applying to these 4 contours. And then we repeat such procedure until we reach MJT here. Then to turn this into a path integral, we just introduce coherent state for each contours and between these operators. So let me call it 1 to 4 for each contour. And then we can arrive in effective action. Let me not go into details of the derivation, but tell you what is important for this effective action. So we now have an effective action on 4 contours. 2 of them are going forwards, 2 of them are going backwards. And this is the form for the effective action. Remember, psi alpha is the Majorana fermion living on each contours. So basically there are 2 parts. One is from the unitary evolution. And this part has a sign -1 to alpha. That is because 2 of the times are going forward and 2 of the times are going backwards. We have also this monitoring part, and it is reminiscent of imaginary time evolution. It does not have this sign structure. This is because we choose the measurement operator to be Hermitian. So the Hermitian operator does not know about the error of time. So there is no such a factor. Now we can look at the symmetry for this effective action. So this is
so the action is describing something to do with the measurements.
That's right.
It's describing the evolution of the state given that you repeatedly measure something?
That's right. So exactly the effective action is this guy. So we have unitary evolution, and then we make measurement. And then we have another unitary evolution, and then we also make measurement. In the end of the day, we take the step to be infinitesimal. So we can write this as effective action.
Do you get something like a quantum Zeno effect when you do this?
Yes, actually we do. So if we consider just if we consider only one density matrix, so there is only 1 and 2, not 3 and 4. And then if this measurement is large enough, basically we will get a pure state. This is the quantum theorem.
So Shaokai, do you mind going back one slide?
Mm-hmm.
So here, no matter how I tune S, this step won't be, you cannot get rid of the measurement, right? So is there a particular reason why you choose this? I mean,
this one?
Yeah, this specific parameterization, or this is just it's not important that you always have some measurement on.
Yeah, I think this is not important as long as you will implement the area law. I mean, the measurement should be like some measurement locally. So,
right. Yeah. So I just meant that in the early on, people do have a limit where things are purely unitary. That's a limit where measurement is completely turned off. But here in this specific parameterization, there is no.
Yeah, there's no way to.
Oh, actually, that's going to be the case when S is 0. Is that right?
But I'm not going to take that limit.
Oh, okay. All right. I see.
Yeah, this S is actually different from this mu. So.
Right. Okay.
Let me not go into the detail, but for this mu, when mu is 0, it is unitary. Mu is something related to S. Okay, so here is the general form for effective action on 4 contours, and this sign structure actually suggests us to separate these contours. So we just put the forward contour together, 1 and 3, and then backward contour together, 3 and 4. Then from this Lagrangian, we can have various symmetry. So if we consider, say, the quadratic Hamiltonian, we only have the hopping. Then we have 2 Majorana hopping here. And this action is invariant under O2 cross O2. So the first O2 is just the rotation between contour 1 and 3. So if you do an arbitrary rotation between 1 and 3, this Lagrangian is invariant. And the second O2 is for the 2 and 4. This is for quadratic Hamiltonian. If we say add a finite interaction back to the Lagrangian, we will have the 4 fermion coupling in the 4 contours, of course. And this 4 fermion coupling will lower the symmetry down to C4. For example, in the 1 and 3 contour, we have such a term, and this term is not invariant under arbitrary rotation between 1 and 3. And it is only invariant under pi/2 rotation. So interaction explicitly lower the symmetry from O2 to C4. Having this symmetry, we can write down the Landau-Ginzburg.
So how does the measurement actually reduce the symmetry if you're measuring random choices of fermions?
It actually does not lower the symmetry. So if I go back, sorry, yeah, this is the measurement. Let me give a more general argument. So because we know what is the outcome of measurement, the measurement operator is same for every control. So basically, these are all the same. So you can like do a linear symmetry between these two and these two.
Yeah. But you said something about the symmetry being reduced.
That is because of interaction, not because of measurement. So
But isn't that action coming from doing these measurements?
Well, there are two parts. One is from the measurement, the other is so for the measurement, there's only two fermion coupling. So this is the projection. Sorry, the measurement used. We can also use many body measurement, but we don't use that.
Oh, I see. So it's coming from the fact that you're measuring like a certain number of fermions simultaneously.
That's right. Yeah, right. So so we have the symmetry. We can write down reflective action, the Landau-Ginzburg theory. What we find that is interesting is the vector representation of the relative O2 symmetry. So it is a vector, and the relative O2 is to fix 1 and 3 components, and then rotate between 2 and 4. So naively, this vector is given by the correlation function. So G alpha beta is the correlation between Majorana fermions in different conforms. So G12 and G14 is the vector we talk about. When we fix 1 and rotate between 2 and 4, obviously we get an angle value. So this is the relative O2 symmetry. Then we write down the Landau-Ginzburg theory, which is nothing but a Z4 clock model. So the first 3 terms have O2 symmetry, and the last term lower this O2 down to C4. So the last term is actually proportional to the interaction because we know interaction lower the symmetry. And another thing is the mass term. So here's the phase diagram. So the mass term is a function of measurement and the hopping. If the measurement is small, so this mu over J is less than 1, the mass is negative. So the symmetry is spontaneously broken. While if the measurement is large, the symmetry is spontaneously unbroken. We can also turn off the interaction, then we have this O2 symmetry. So in the symmetry broken phase, we have this ghostmode mode for the non-interacting case. Having talked about the Landau-Ginzburg theory, then what is the consequence of this symmetry breaking? So one way to see the consequence is the Renyi-to entropy. Renyi entropy is expectation value of swap operator. So let's divide the system to A and B 2 parts and consider Renyi entropy of subsystem A at time t, capital T. So what we need to do is to apply swap operator to subsystem A at time t and apply identity operator to its complement B. And the swap operator will change the boundary condition. So I will regard this boundary of time as the boundary. So in complement B, since there is no swap operator, so it's ordinary trace. So we just connect each density matrix separately. In subsystem A, because of the swap operator, it leads to such connection. We connect 1 to 4 and then 3. We call our order parameter is given by correlation. So for complement B, because G12 is non-vanishing, the angle is 0. So for the complement B, the angle theta is 0. On the other hand, in subsystem A, G14 is non-vanishing, so the angle is pi over 2. So in order to calculate the Renyi entropy, we need to apply the boundary condition twist of the angle in the boundary of A. Then the Random entropy is given by the free energy difference between the configuration with the swap operator and without the swap operator. Now we have all the knowledge to say dynamical symmetry classifies different entanglement phase. So in a symmetry broken phase, vectors are ordered in the bulk. And let's see what is the consequence of the boundary condition. For quadratic Hamiltonian, we know it is an O2 vector. So this boundary condition actually creates two half vortices given by these red dots. So if you go around this red dot, the vector will rotate by pi/2. So this is half vortex. And the Random entropy is given by the free energy of vortices, which is well known to be log L. And this explains the logarithmic entanglement entropy in the monitor-free formulas. For finite interaction, we know symmetry is lowered to a discrete C4 symmetry. So the boundary condition creates domain wall instead of vortex. And then the free energy of domain wall is enhanced to be linear in its length. So it implies a volume law entanglement entropy.
So for the first case, I'm wondering about, or I forgot if people have done that already. So the coefficient in front of the log, in the language of superfluidity, that's just the superfluid stiffness. And I suppose if the analogy is correct, then what happened is that if you start from the disorder phase to go into the order phase, there's a universal jump of the stiffness, and then it grows continuously as we go deeper and deeper into the order phase, or KT phase, if you will. And has anyone studied that kind of stuff before, or either numerically or analytically?
Yeah, we actually calculate this coefficient, but in our case, it changed smoothly.
Meaning it's starting from 0?
Yes.
So, oh, I see.
Yeah, I will show you the result later.
I see.
So in symmetry unbroken phase, the vectors are disordered in the bulk. As a result, the boundary condition can only change free energy locally. So the Random entropy now is a constant. That implies area law. So now, in summary, dynamical symmetry classifies the entanglement phase. If symmetry is spontaneously broken, we have a volume law or area law, depending on the interaction strength. If the symmetry is unbroken, we have area law. And this is a plot. So it's Random entropy per length versus measurement. So we find a transition from volume law to area because it's entropy density. So for the volume law, the entropy density is finite, while for area law, entropy density is 0. So the transition is exactly at 1. We can actually do better. So dynamical symmetry can predict a critical exponent if we focus on the transition point. So let's first look at the non-interacting case. This is the coefficient in front of this law. So the power is 1. And here I plot the half-chain Random entropy as a function of the length of the chain and at various measurement rate. So if the measurement rate is small, it is a log function, while if measurement is large, it saturates with area. If we plot the data near the transition point and use this critical exponent from the equation, we can get a very good data collapse.
So, sorry, maybe I have a question here, or multiple ones. So the calculation, the numerical calculation is done within the SYK framework, right? So taking the saddle point and do all those calculations.
That's right. That's right.
It's not really taking however many Majorana fermions and really projective measurement, that kind of numerics. Okay. So, and the other thing is, for 2-dimension, if there's really an O2 transition, naively, if it's KT, we know it's not one. So
Yeah, sure.
Right.
This is the mean field actually. So
this is
I take large N.
so you're saying the large N makes it not KT, but just like a mean field XY transition?
That's right. Exactly.
I see.
And
Okay.
I should not use this new here, because in phase transition new has another meaning. But I just use this to indicate the coefficient in front of skatings.
Oh, so you specifically mean how the coefficient of the log changes?
Yes, and
Okay.
that's right. Sorry to cause the confusion.
A quick question. So the vertical axis, let's see. So can you remind me, is S the trace of rho squared?
Yes, that's right.
So S equals 1 corresponds to no entanglement.
Mhm.
That's right.
Oh, sorry. S is minus log the square. So S is second Renyi entropy.
Okay, so S equals 0 corresponds to no entanglement.
Mhm.
But I would think that as the rate of measurement gets very large, then that should kill all of the entanglement. Right. So you're seeing that this thing is plateauing at 1 in that upper left diagram, the one that has that like horizontal, that's when you like measure really rapidly. But I would think that when you measure really rapidly, that would kill all of the entanglement and it should go to 0.
Yeah. So actually, you are right, and this plot is actually very close to 1. So the measurement is not that large. But if you increase the measurement, say to infinity, then absolutely you get 0.
Okay. And okay, good.
Yeah. So for this C4, so if the interaction is finite, we get C4 instead of O2, and the critical exponent also change from 1 to 1.
So just to make sure, so here, I guess everything is supposed to be proportional to N, but you just didn't write it, I guess, right? Just to make sure.
Yeah,
Okay.
that's right. Exactly.
Okay.
Okay, so yeah, the last consequence I will talk about is the ghostmode mode. So for quadratic Hamiltonian, we know the symmetry is continuous. So the symmetry broken phase has gapless ghostmode mode, and we call the vector is the relative rotation. One consequence of the ghostmode mode is, of course, the logarithmic entanglement entropy. The other consequence is that it coupled to other fluctuations. So it coupled to G13, for example. So G13 is a correlation function of fermion between 1 and 3. And this is the coupling between G13 and ghostmode mode. So for ghostmode mode, its mass is 0. So K is the momentum. And for G13, nothing forbids a finite mass. So in general, it has a finite mass M. And the coupling between G13 and theta is actually proportional to the frequency. And this has a symmetry argument, but let me not go into details of symmetry argument. So in the end of the day, we get a correlation function for G13, and because of its coupling to the gapless ghostmode mode, the correlation becomes gapless as well, but it has a different correlation from this ghostmode mode. So how can we see this correlation? We can consider equal time correlation function for fermion. So we evolve the density matrix, and then we apply Majorana formula at psi 0 and also at psi r at equal time. I just draw this for illustration. So they are at equal time. And this is the definition, of course. And then if we take the average, I mean average over measurement outcome, as well as average over the Brownian randomness, this is 0 because it just averaged out. However, if we consider square of this guy, correlation square, then the fermion can excite G13 field. And because it coupled to Gabley's ghostmode mode, the correlation of the square correlator will be power law-like. And this explains a various numerical calculation for observing this power law decaying correlation square. So yeah, that's basically the first part. So now let me move to the second part, the quantum air. Hybrid circuits have a quantum information interpretation. It can be understood to generate an error correction code. Say S is the system. So here is the monitor SYK circuit. And we just store information in the circuit and evolve. At the end of the day, we get an error correction code. This is the interpretation. And we also introduce measurement apparatus here just for convenience. So with this measurement apparatus, before the measurement, it is prepared to be 0 state. And if the ice measurement is applied to the density matrix, we also change the state from 0 to I. An important thing is this apparatus is not an error. It actually collects the measurement record, which is sort of classical information. And people can ask about quantum channel capacity of such circuit. And it has been shown that the capacity is exactly given by entanglement entropy averaged by the Born probability. So in this context, measurement-induced phase transition, more precisely, measurement-induced purification transition, is a transition of quantum channel capacity. So if you fix a finite density of information in a circuit, and there is a transition as a function of measurement rate, and it is distinguished by the capacity. So in a reversible dynamics, the capacity is finite, so you can have a residue information that can be decoded successfully. On the other hand, in reversible dynamics, the decoding fails. So the second part of this talk is about the effect of quantum error. The language of quantum error is also the quantum channel. We need a set of Krauss operator. For example, the depolarizing channel has a so this channel gives you a identity with some probability, and this can be written for a qubit by a set of Krauss operator given by the Pauli matrices. So in our case, we model the error as loss of measurement record. So we know there is a measurement apparatus that collects the measurement outcome. If we lose the measurement record, we just need to trace out this measurement apparatus. And the result is applying a set of Krauss operator to the density matrix, which is very similar to the error here. Another thing of the error is that it can happen anywhere. It can happen during the encoding or at the end of the encoding. So our question is there a systematic way to understand the effect of errors? So the first thing to know is the quantum error explicitly breaks dynamical symmetry. If we keep the measurement, we know exactly which measurement operator is applied to on the contour. And we have two independent symmetries in 1 and 3, as well as in 2 and 4. If we lose the measurement record, we don't know which measurement operator is applied to this density matrix. As a result, we need to sum over all possible measurement outcome for these two density matrix separately. So there are two independent summation for these two density matrix, just because we don't know the measurement record. And the consequence of that is that the relative symmetry is explicitly proven. Recall, for example, the relative O2 rotation is to fix 1 and 3, and then rotate between 2 and 4. But now we have two independent summation. 2 and 4 can be different. So this explicitly breaks the relative symmetry. So to be concrete, we use a slightly different monitoring operator. But this, we couple the SYK model to the apparatus by a jump operator. The jump operator is this annihilation operator for the complex fermion. But this is not important. The important thing is the error breaks the relative rotation symmetry explicitly. So recall the order parameter is given by correlation function between different contours. And also this record loss will actually generate coupling between 1 and 2 contour, as well as between 3 and 4 contour. This is because we sum over the measurement outcome separately for these two density matrices. The result of that is we have a linear coupling in G12 plus G34. And this is nothing but phi 1. So we have this Landau-Ginzburg theory, almost the same as before. The effect of the quantum error is the last term. So it is a linear coupling to phi 1. And the strength of that is proportional to the probability of losing a measurement record. And it is like a magnetic field pointing along phi 1 direction. Then what is the consequence of such quantum error? So if in the bulk we have lost the measurement record, then the consequence is the absence of measurement induced phase transition. This is because in the presence of the field, the vector in the bulk is pinned to angle 0 in the bulk, while it is pinned to angle pi over 2 in the boundary. And there must be a domain wall separating these two domains. And this is irrespective of measurement rate. Even in the symmetrical phase, still we have the domain wall. So like before, I plot the Renyi entropy per length as a function of measurement rate. If there is no quantum error, we have measurement induced phase transition as before. But if I turn on finite probability of losing the record, you can see the Renyi entropy per length is always finite. So the transition is gone just because the magnetic field explicitly break the symmetry. We can also plot the Renyi entropy per length as a function of quantum error at the transition point. So if there is no quantum error at the transition point, Renyi entropy density is 0. We can see it is linearly proportional to the probability of losing the record, which is consistent with the field theory, the linear coupling with the field theory.
I have a question. Is this magnetic field term non-Hermitian?
No.
So it is Hermitian. So how can it lead to entanglement loss?
Let me think. Sorry, it is non-Hermitian. It is actually coupling between 1 and 2. Okay, this is like open quantum system if you only consider one density matrix.
Right, but that term H phi 1, so is phi is that order parameter. I see. I mean, normally a magnetic field term would be Hermitian, though, right?
Yeah, but here it is non-Hermitian. So H is real, of course, but if it enters the action as exponential minus I, so it actually decreases the weight of the partition function of the action.
So then it's not exactly like a magnetic field term then, right? But I mean, if I have a magnetic field.
Well, if you have a real magnetic field, then you will have IH.
Oh, okay.
IH in 1 and minus IH in 2.
Got it.
Maybe, sorry, I thought that doesn't really solve the problem, because if I just stare at the Landau-Ginzburg theory and assuming every single parameter is real, it looks unitary in some sense. And
yeah, it looks unitary in some sense.
How do I know that the H term is not unitary, or it's really, you're saying that there's some emergent unitarity at the critical point? Or I should really say H is supposedly purely imaginary in this theory.
I think when you write the theory in Keldysh contour,
right,
and if it is unitary, then you will have a sign structure. So we have e to minus IH t, right? In 1, e to IHT in 2. And this, so basically it is an imaginary number because IH is imaginary.
Right, so that's the non-unitarity.
No, that is unitary.
Sorry, oh, that's okay.
That is unitary, and then here we instead, we don't have this I.
So you're saying every single term is non-unitary here.
Well, I mean, what I'm saying is that you cannot take a Hermitian conjugate to this quantity, because when you take Hermitian conjugate, you need to swap the different contour as well. So the Hermitian conjugation is not just Hermitian conjugation in operator sense. You need to change the field in different contours. Say you change it 1 and 2, this will lead to some consequences.
I see. So I guess maybe then it's fair to say that this apparent unitarity in the theory is not anything UV, but it does look like a unitary theory in certain sense. Maybe we call it emergent unitarity or whatever, but it's not related to the unitarity of the pair problem.
Yeah.
Okay.
That's fair. Okay, so let me move on. So another consequence. I think I'm running out of time.
Yeah, we had a lot of questions, so but.
Okay, maybe let me wrap up really quickly. So another consequence of the magnetic field is the pinning of domain. So we consider Renyi entropy of system A. Suppose the ratio between LA and L is A and is little a and is larger than 1/2. So this is a schematic plot of the boundary condition. So minus means swap operator and plus means identity. Or you can say minus means phi 2 direction and plus means phi 1 direction. So what is the Renyi entropy of this configuration? There are two possibilities. If the vector in the bulk is pointing minus, you have a domain wall enclosing A bar. On the other hand, if it is pointing plus, you have a longer domain wall. And free energy is apparently given by line tension times the length of the in the leading order. So in this case, the first configuration always wins because it has less free energy. The domain wall is shorter. However, if we consider quantum error occurring at the end of the circuit, that means magnetic field exists near the boundary. So let's say the width of where the magnetic field exists is TH, and in this blue regime there is finite magnetic field, and the magnetic field is pointing along plus. It is pointing along the phi1 direction, and the change of free energy is given by these two formula. So in the first configuration, these vectors are unhappy because of the magnetic field. So you will pay a penalty of this unhappy vector, while in the second case, it is independent of magnetic field because the vectors are happy with the magnetic field. Then there's a pinning transition induced by magnetic field because the first one is linearly proportional to magnetic field, while the second one is largely independent of that. So there is a critical field. So if the magnetic field is smaller, then the first one also wins. But if it is larger than the critical value, to change the dominance. So here is a plot. The Random entropy in terms of the quantum error in the boundary. So apparently, so this orange dots are for first configuration, and these blue dots are for the second configuration. And apparently, you have exchange of these two domain walls. And we have the relation of this pinning of domain wall to the error correction threshold. So we imagine we encode information using the circuit. Here we separate the circuit into A and B two parts. Say we have full control of A qubits and we store information in A qubits. For convenience, we also introduce a reference, which is maximally entangled with A. And we also imagine this error occur at the end of encoding. So we couple the circuit to the environment at the end of the circuit. And the criteria for successful decoding is mutual information between the environment and the reference being 0. Then we can basically calculate this mutual information one by one. So for entanglement entropy of reference system, we need to apply swap operator to the reference. And the effect of swap operator is to change the boundary condition in the bottom edge. While for the environment and the system, we don't apply the swap operator. So the top edge is boundary condition is plus, and the magnetic field is also pointing plus. Then the configuration has only one domain wall, and this is the Random entropy coming from free energy of this domain wall. To calculate entanglement, so Random entropy of environment, we need to apply swap operator to environment. And the effect of this swap operator will flip the sign of magnetic field. So the vector in the bulk is pointing to plus if the magnetic field is small. And there is no domain wall here, but we need to pay the penalty of this unhappy vector. For the last Random entropy of this environment and reference, we need to simultaneously apply a minus boundary condition in the bottom edge, as well as flip the sign of magnetic field, because we apply swap operator to both E prime and R. And the result of that is a domain wall and these unhappy vectors. So this is the free energy of that. But there's another possibility, that is the bulk vector pointing toward minus. And for this configuration, we don't have worry about the domain wall and the penalty because all vectors are happy. We need to pay the penalty of this long domain wall separating the boundary and the bulk in the top edge. So the competition between these two configurations result in an error threshold. So if the magnetic field is small enough, the first configuration wins. And the mutual information is 0. So we can safely decouple the system from the environment and then decode the information in the system. However, if the magnetic field is large enough, there is a pinning transition, as we saw before, and the mutual information now is finite. So this signals a error correction transition. So basically, that is what I want to talk. And thank you for your listening.
Okay. Thank you, Shaokai, for the wonderful talk. And yeah, we are open for questions. So even though I have asked quite a bit, still some other question. So I guess all these studies, in a sense, make specific use of the two replicated model, right? So especially the O2 and the C4 symmetry involved.
Right.
And but if we were to really try to deal with the proper average ensemble, one have to do replica limit and all those stuff.
That's
And
right.
the big issue is that the symmetry would change completely. And is there something about SYK that makes it special, that two replica, you know, that the two replica already tells you everything that?
Yeah, actually there is a hidden slice about this. So here's a very brief outlook. So the range entropy calculated by the statistical model is given here. So we have actually trajectory, quantum trajectory average in the numerator as well as in the denominator.
Yes.
And this rho theta is actually a normalized density matrix. So in this case, we can map second range entropy to the free energy of configuration with and without boundary condition. However, what is really matter is range entropy averaged by Born probability. So this last factor is the definition of range entropy, and we weight this by Born probability, and then we average the measurement outcome. So these are definitely different objects. Important observation is that they coincide when n is equal to 1. So this is, they both give the entanglement entropy. And this opens up a possibility to take the replica limit. So let's look at the quadratic Hamiltonian. And if we take all the odd contour together and the even contour together, and this Lagrangian has O2 cross O2 symmetry, then the question is, what is the implication of this O2 cross O2 symmetry to the measurement induced phase transition? And what is the effect of interaction, blah, blah, blah. And this is the, it's a future work.
Yeah, another question that I have associated actually exactly the Lagrangian that you're showing here, well, without the interaction term, but this looks really a lot like Maldassana Chi. Like, I think you know what I'm talking about. This this wormhole setup where two SYK clusters are coupled together. Are there some part of the story that you told us has any connection to that story?
That's a very good question. Well, it is not that Lagrangian.
Because the
So
coupling.
if you take the mu to be imaginary, then it's the same.
I see.
So it is the non-Hermitian part of non-Hermitian version of the model.
I see. Are there other questions from the audience? Okay, I guess if not, then yeah, let's thank Shaokai again for the talk. And yep, that'll be the end of the seminar today.
Thank you.
Thanks, Shaokai.
Thank you for your attention.
Yeah, actually, I somehow noticed that Maryland is growing really quickly in terms of just size, like number of people there.
Really?
I have the, or maybe it's just that the people that I have at least heard the name of, and or maybe it's just that the people that I'm aware of working on similar stuff. I know that the Nicole just joined, right? Nicole Hopper, is that her name? Her last name?
I don't know.
Oh, okay.
It's like a
And
what is she doing? I mean,
she
not
does a lot
measurement.
of well, some of it is like quantum thermodynamics.
Maybe
And-
he's joining JQI.
Yeah, I said
There are two
I think of
institutes.
Maryland as a whole.
Yes.
But yeah, I understand you
Oh,
guys
I see.
are different institutions. Yeah.
Mhm.
You're with CMTC.
CMTC, that's right.
I see. Okay. Yeah, and also Michael Gollins is there, right?
Oh, yeah, that's right.
It's gonna be fun. Well, but you're leaving soon, so it's also fun. So,
I don't know. Let's see.
but you're gonna actually move, right? Since it's looking like things is gonna be open.
Mhm.
Okay.
Mhm.
Right.
Okay.
Thanks again for the
Yep.
talk. See you.